Okay, hi everybody. So what we're going to be looking at today is kind of a continuation of what we did yesterday in that we want to figure out is there some ideal height that an archer could be so that they get a bullseye every single time without even having to like aim anything, without having to be like, oh, like that. You know how you do when you make that noise when you aim. And then can we use a linear graph to help us determine this? So yesterday we looked at how we can create linear graphs, some graphs that may not inherently be linear. And then what we're going to do today is just kind of look at this archery situation really quick. I'm going to give you a brief review about kinematics. Hopefully it won't be too long. And then I'll cut you free, and you got a Google form, experimental design and archery graph Google form that I want you to try out. That will be due. So just kind of, again, to reiterate the situation, we want to be able to kind of drew it out. We're going to say, hey, the initial velocity for an archer is about 67 meters per second or 150 miles per hour. So let's assume that we can shoot that perfectly every single time. And we want to then figure out like, hey, what height could this person be at so that they, like over here is kind of the height, the starting height of the arrow. Is there a height that they could hold it so that they can just perfectly shoot it horizontally every single time, no aiming, so that 70 meters away it would hit a bullseye. So that's what we want to look at. So really quickly, I just want to review kinematics, kind of talk over all these ideas. So kinematics is really just the study of a motion of an object. And one of the main things we want to think about now that we're reviewing for this AP test and kind of going over all this content again is when do we actually want to use this? Like when is kinematics actually useful to us? So we want to use kinematics anytime we're analyzing the motion of an object. So if we're analyzing something about its position, its velocity, its acceleration, the time that it's traveling for, kinematics is going to be a go-to for that. Sure, later on we develop some ideas that are a little bit easier to work with, like energy or like graphs with energy. But if we have something about the position, velocity, acceleration, and time, then this is going to be a go-to. Also, whenever we're doing projectiles, projectiles is really the best, or kinematics is the best way to analyze projectiles. So if we're doing projectiles, kinematics is going to be one of our go-tos. But really, whenever we have something moving, kinematics can be a tool in our toolbox that we use to solve kinematics problems. So just a few terms before we get started. We have the position x, its variable is going to be x, and that just tells us an object's location in space, so where is that object at? Time is pretty good because we use time colloquially, and it means the same thing. So time is just the number of seconds that have passed, how much time is going by. To kind of get more into our equations and our terms, initial position, x naught, is going to be where is the object located right when we start our timer. So right when we begin timing, where is our object? Then the velocity v is just how fast is an object moving, how many meters has it traveled each second. And then to get a little bit more specific with our terms, usually these will be more delineated when they show up. They'll be a little bit more specific about them. So distance is the total ground an object covers. It doesn't care what direction you're going. It just says, hey, how many steps did you take? If you were wearing like a Fitbit, it would be like, oh, this many steps. It doesn't care that you went left and then right, then up and then down if you're going down the stairs. It just says, how many meters did you cover? How much total ground did you cover? Then the displacement is really going to be your final position minus your starting position. So your space between your starting and ending point, direction with this matters. So an example of this is like, hey, you get out of your bed, you put on your Fitbit, you walk around your house a little bit, and then at the end of the day, you'll get back in bed, and hopefully your displacement will be 0 meters. You start and end at the same place at the start and end of the day. And then your speed is just going to be how fast you're going without a direction, so distance per time. Then your velocity is going to be how fast an object is moving in a direction, so your displacement over your time. So velocity has a direction to it, and speed does not. And now just kind of going into what we did when we studied this. So we are we're very familiar in math by doing constant slope equations, this slope form, this y equals mx plus b linear equation, where y stands for our vertical axis, x is whatever variables on our horizontal axis, m is our rise over run, our change in our y-axis versus our change in our x-axis, and then b is our y-axis intercept. And then now what we're going to do, when we did this in class, we did those buggies and we had that graph that we made. So we graphed position versus time. We saw we had this nice constant line. So when we're looking at objects that have a constant velocity, we can start to put some physics ideas into our math ideas. So instead of y on our vertical axis, we have our x, our position, on our vertical axis. So instead of y, we can graph position, and we'll graph that in meters. Instead of x on our horizontal axis, some random variable, we can graph time on our horizontal axis. So how much time is going by, how much time is elapsing. It makes sense to put time because it's kind of like time is always flowing, time is always going to the right. And then, yeah, so then we can say, hey, we defined our initial position to be whatever position we're at time of 0. And then we define our velocity to be our change in position over our change in time, which if we look at this is the change in our vertical axis over our change in our horizontal axis. So our velocity is really our slope. So our velocity is measured in meters per second, and it's the slope of our line. So then we can plug this into our situation, our kind of y equals mx plus b form, and say x equals vt plus x naught. So instead of y, we're putting x, our vertical axis intercept. Instead of our slope, we're putting v. Instead of our horizontal axis, we're putting time, and then x naught for the y-intercept. So we're just being a little bit more specific. And then here's just kind of what those all mean. So we've been over this before. I'll just kind of leave this up if you want to pause it and read it, but it's really what I just went over. And then we said one big idea when we have this constant velocity graph and model is the slope is going to tell us the velocity. So if our slope is negative, it means that our object has a negative velocity. It's traveling in a negative direction. If the slope is positive, it means that the object is traveling in a positive direction. And the steeper the slope, the faster our object is moving. So it means it's covering more meters per each second. So if we look at these, we're comparing red and blue. Red has traveled 2 meters in 2 seconds, whereas blue has only traveled 1 meter in 2 seconds. So red is traveling faster than blue. So our slope is going to tell us about the velocity of our object. And then one thing that's important is sometimes we want to graph velocity versus time. We want to figure out how does the velocity change over time, and we want a nice visual for that. So what we can do is if we have a position versus time graph, we just said the slope is going to tell us the velocity. So we can calculate the slope, we can solve it, and then plot it on our velocity versus time graph. So we're pretty used to this by now. We're kind of comfortable with it. Here we're seeing, our slope is just going to be 1 meter every 1 second, 1 meter, 1 second. So we can say throughout this 6-second time period, our velocity is just going to be a constant 1 meter per second. So we can graph that, and we can visualize how the velocity is changing throughout time. And then we can also go backwards. So this one's a little bit trickier, so I'm going to kind of walk through the steps. But so if we are given a velocity versus time graph, we can look at it and say, okay, if we're thinking about this, if we don't even look at the graphs right now, if we just kind of think about what our graphs mean. So if we're going 2 meters per second for 1 second, how far would we have gone? And we can calculate that pretty quick. We can do 2 times 1 and figure out, we went 2 meters. And then if we were going 2 meters per second for 2 seconds, we would be able to multiply those and say, we went 4 meters. And if we went 2 meters per second for 3 seconds, we went 2 meters, 2 meters, 2 meters, so we went 6 meters. So if we graph that out, we'd say, this would look like us being like, okay, we were at 2 and then 4 and then 6. And so we kind of did that math, and we were able to figure out how far we went, even though all we had was velocity and time data. So what we really were doing without realizing it is we were finding the area under our velocity versus time graph. So this is kind of straightforward when we have a nice constant velocity. So then again, we're doing that. So this is straightforward when we have a constant velocity, but eventually we'll get these changing velocities, but this idea still applies. So this idea, the area under velocity versus time graph, tells us the object's position at that time is very important. So we can look at the full area from 0 seconds to that designated time and figure out, hey, what position are we at? Where did we end up? And then we're going to look at situations. That's kind of our basics for constant velocity. If something has a changing velocity, the ideas still apply. It just gets a little bit more complicated. So if we have objects with constant acceleration, so some sort of changing velocity, we talked about getting these equations. So we're used to these equations. I won't walk through them, but we have an equation to figure out the position after some amount of time, and we have an equation to figure out the velocity after some amount of time. And so when we accelerate, we really say this is an idea that's the rate of change of an object's velocity. So how is our velocity changing? So if an object is changing speeds, that just means that it's accelerating. If our velocity changes, our object is accelerating. The units of acceleration are just meters per second per second. So how many meters per second is your velocity changing per second? So that's kind of one way to think about it. How is your meters per second of your object changing each second? And then it's meters per second, or we can call that meters per second squared. And before, when we were graphing, we looked at situations with constant velocity. The ideas about our graphs still apply. Now what we have to do is just kind of find the velocity at each instant, the instantaneous velocity, for us to graph velocity, because our position versus time graph will be changing. So now when we're doing it, we have to look at the slope at each given time. So if we're in calculus, maybe we're thinking, oh, that means we have to use derivatives. We have to find the actual value of the slope. We won't have to. We'll just have to look at it qualitatively and say, will it be going faster, slower? Will it change directions? Has it stopped? What's going on with the actual position versus time graph at that moment? So, well, let me look at this really quick and go back. So if we're looking at something like this position versus time graph, we can look at this and say, well, at A, it looks like I can kind of put a pencil down there and kind of trace that out. But it looks like I have a positive slope. At B, it looks like my slope is kind of at 0. At C, it looks like I have a negative slope. So it looks like I'm going in the positive direction. I'm slowing down because my slope, my velocity went to 0. And then my slope, my velocity, is now getting negative. And then at D, we're going to say, oh, okay, well, it's getting negative again. It's still negative. At E, I still have a negative slope, so I'm still traveling in the negative direction. Or I still have a negative velocity. And then, yeah, we can see, oh, I'm going in the negative direction. At F, I've stopped. And at G, I'm walking in the positive direction. I'm going back towards 0, which checks out what we see on this graph. But so when we're looking at this, the positive slope means the object is traveling in a positive direction. It has a positive velocity. A negative slope means the object is traveling in the negative direction. It has a negative velocity. 0 slope means we have a 0 velocity. If our slope is steeper, it means we're moving faster. And if our slope is less steep, then it means we are moving slower. We're covering less meters each second. And then kind of the same idea, we can just extrapolate it further. The slope of a velocity versus time graph tells us about the acceleration. So if we want to know about the acceleration, we can find the slope of a velocity versus time graph. And after we find the value of that slope, we could graph it if we wanted to, like we see in this image. We have a velocity of 1 meter per second each second for our increase. So we go from 1 meter per second to 2 to 3 to 4. So we are changing our speed by 1 meter per second each second, which stands for an acceleration of 1 meter per second squared. And then again, we can go backwards, where the area under an acceleration versus time graph is just going to represent our velocity at each time. So to kind of summarize our graphing, if we have a position versus time graph, we can figure out the slope to go to a velocity versus time graph. If we have a velocity versus time graph, we can figure out the acceleration versus time graph by finding the slope. If we have an acceleration versus time graph, we can figure out the area underneath to go to velocity versus time. If we have a velocity versus time graph, we can figure out the area to go to our position versus time graph. So we go slope if we want to go up, area if we want to go back. So this is just a nice little look at that. If we want to look at the units too, we see that the units totally check out. If we have a position versus time graph, our units of slope is position over time, so meters per second, and that's our units of velocity. If we have a velocity versus time graph and we look at that slope, that change in velocity over that change in time, we have meters per second, which is our units for acceleration. So then we get acceleration. And if we go backwards, we see that same thing. We see that same pattern where the units check out. And then finally, just a quick little thing about projectiles. So projectiles are important because it's really us taking our ideas of kinematics and just doing them twice. And there's a few little things that we have to remember when we're doing projectiles, but really it's just us doing kinematics, but 2 times. So here we have this picture where we have a ball that's launched and a ball that's dropped. We see that they're falling at the same rate, even though one has been launched and one is dropped. So we kind of did this demo in class. But we see, hey, these are falling at the same rate. It looks like what's happening in the y direction then is pretty much independent of what's happening in x because they're falling at the same rate. If they were falling at different rates, then we'd be like, oh, okay, the x direction stuff has messed up that yellow ball, but that's not the case. So the main thing we have to do with projectiles is this saying, because we have an acceleration in the y direction, but not in the x direction, we got to keep them separated. So we did that a bunch. We got to separate the x direction and the y direction. So here's just a nice little picture about that. We can say every projectile path is made up of something happening in the x and something happening in the y direction. So we have the x direction and the y direction, and when we combine them, we see the full projectile motion. But we can really think about it as something in the x and something in the y. So if we do want to separate that velocity, if we have a velocity that's in some sort of direction, like we have in this image up here, if we have it not purely in the x direction or purely in the y direction, we can just use trigonometry to split that up. So we can kind of draw in the velocity in the x direction, the velocity in the y direction, define that middle thing as the angle, that angle in between, and then we can figure out, using trigonometry, values for our velocity in the x direction and velocity in the y direction. So really the main thing with projectile motion is it's really the same thing, but we're just doing it twice. So the only difference is now we have two directions to deal with, the horizontal and the vertical. So whatever's happening horizontally is independent of whatever's happening vertically, except for they are linked by that idea of time. So they're linked, the amount of time in the x direction has to equal the amount of time in the y direction. So in the horizontal direction, a few key things to remember is that when we're in the air, the acceleration is just going to be 0 meters per second squared. There's no forces that are forcing it in the horizontal direction. So there's nothing really changing our speed there. So we have no acceleration in the x direction. And then the time it takes to travel in the horizontal direction is the same as it takes to fall in the vertical direction. We just talked about that. And then vertically, if we're in the air, if we're on free fall on Earth, then our acceleration is going to be negative 9.8 meters per second in the vertical direction. And that happens as soon as it hits the air. As soon as it's in the air, the force of gravity changes in object speed. So right as soon as we launch in that projectile path, we have acceleration in the y direction. So the time it takes to travel in the horizontal is the same as it takes to travel or to fall in the vertical direction again. So yeah, that's kind of our ideas. Again, another key thing that I didn't put in here, but is if we say that we drop an object, that means your initial velocity in the y direction is just going to be 0. So that's another thing to keep in mind. And then finally, a lot of what we do on the AP test is it asks us to make experiments. So if we're going to measure these variables, here's the tools we want to use to do that. So we want to measure x, we can say, hey, you can use a meter stick for that, or we can use a motion detector. If you want to measure velocity, you can say use a motion detector, or instead of directly measuring it, you can say, oh, I can calculate it by figuring out the change in distance over the change in time. If you have a acceleration and you say, I want to measure this, you can use a motion detector to measure it, or you could again say, oh, I'm going to calculate it with a meter stick and a stopwatch, but that's a lot harder to do. For time, if you want to figure out time, you can say I can measure that with a stopwatch and I can measure that directly, or you can say like a slow motion camera and you can count frames on there, however exact you want to be. And then an angle, if sometimes you're doing projectiles and you want to know an angle, then you can say you can use a protractor for that. So that was just a brief review of kind of everything that we've done with kinematics. Hopefully it was just a nice refresher. I feel like we've done these a lot, so hopefully they've kind of been fresh in your mind, but hopefully that kind of rekindled some stuff. So what we're going to do now is we'll check out the Google form about this archery idea and see if we can use these ideas and linearization to figure out what height an archer could be so that every time they could get that bullseye without having to like aim up or down or anything like that. All right, so that was a brief little review. Hopefully that was kind of helpful.